Hello and welcome to our next tutorial on the Opamp parameters and ideal characteristics of Opamp. So in the last video we have talked about the introduction of operational amplifiers, it's a differential mode and a common modes. So let us look into the parameters of Opamp. So there are 9 parameters of Opamp, that is open loop voltage gain, common mode rejection ratio, maximum output voltage swing, input offset voltage, input bias current, input offset current, input impedance, output impedance and sleeve rate. So let us talk about each of these individually. So first one is the open loop voltage gain. So let me clear this. So open loop voltage gain is nothing but that we have discussed in the previous video, that is the differential mode gain is same thing, we call it as a open loop gain. So this is, in short, it is called as AOL, open loop voltage gain. A stands for gain, OL stands for open loop. Now in the previous video we have seen that, for example, if we are connecting an voltage source across the inverting and non-inverting terminal, the output will be the amplified version of the signal, or it might be a for example, let us take this case where this is V1 and V2. We are connected with two different voltage source, sinusoidal voltage source. This is inverting and this is non-inverting terminal. So in this case the input is 0° phase shift and this is 180° phase shift. This is double-ended differential mode case. So what happens in this case? So both since this is connected to an inverting terminal, the voltage when it appears across internally, so it will change to 180°. There is a phase shift of 180°, and this will be added with the voltage of the V2. Then finally this output voltage will be an amplified version of the sum of two inputs. So basically this gain which is multiplied with AV, this added inputs multiplied with AV, so that's why it is called as an open loop voltage gain. An AOL of an op-amp is the internal voltage gain of the device and represents as the ratio of output voltage by input voltage. So basically it is represented by sometimes with CMRR. So let's talk about what is CMRR. The second op-amp parameter. CMRR is nothing but the common mode rejection ratio. It is the ratio of the open loop voltage gain to the ratio of common mode gain is a CMRR. So let me clear this section. So CMRR is nothing but a ratio of an open loop gain by a ratio of a common mode gain is CMRR. So ideally the value of CMRR should be very high, because when we talk ideally the common mode gain should be 0. So what is this common mode gain? We already discussed in the previous video that, for example, if we apply the input with of same phase at both the inputs, then what will happen? Let us take this example again here. So we applied the input at V1 and V2 with same phase and same amplitude. Then due to this, what happened here, the output across V1, it's get inverted by 180°. So we will get a signal like this, and the second signal at the non-inverting terminal, it is like this. So when you try to add this, so this is nothing but ultimately we will get an output is equal to 0. If there is a slight variation in terms of magnitude, so whichever will dominate, we will get an amplified version of that input across the output. So that is CMRR, and that gain we call it as ACM. So if there is no, if both the input magnitudes are equal, then the output is 0. If any one of the input magnitudes are different, then we will get the magnified version of that corresponding inputs. So ideally it's supposed to be 0, but practically there will be a small ACM value which is exist in most of the op-amps. So CMRR is defined as the ratio of AOL by ACM, and the common mode rejection ratio is nothing but it is an ability of an op-amp to reject the unwanted signals of the same polarity which appear across the input with the same polarity at both the inputs. So that we call it as common mode rejection ratio. So in terms of dB, if you want to represent, then it is CMRR will multiply with 20 log. CMRR is equal to 20 log of, that is AOL by ACM. So this is represent, the CMRR is represented in terms of dB. So ideally the for open loop voltage gain, the CMRR value will be in terms of 2 lakhs, or it might be 1 lakh to 2 lakh. So it means that the desired input signal is amplified by 1000 times more than an unwanted signal or unwanted noise. So let us take a small example here. So here, let's take an example. A certain op-amp has an open loop differential voltage gain of 1 lakh and a common mode gain of 0.2. Then determine the CMRR and express in dB. So open loop gain is 1000 and ACM gain is 0.2. So what is the CMRR? It's a simple straight away calculations from the formula, that is then we get a CMRR is equal to 1 lakh by 0.2, which is equal to 5 lakhs. Okay, in terms of dB, when we multiply with 20 log, we will get this as 114 dB. This is a very straight away example which we can calculate. Now let us come back to our parameters. Now let us talk about the maximum output voltage swing, or generally it is called as output voltage swing. So when an input voltage is applied, ideally this we already discussed when we were talking about in the previous video, that let me take the same example again that we had discussed in the previous video. So here we are applying, let us take one more example where I'm applying a DC voltage. So here I'm applying a 4 volts and here I'm applying a 4.2 volts, and let us consider the open loop voltage gain, that is AV, is equal to 1000. So with respect to the output voltage equation V0, so our V0 is nothing but AV with a difference of V2 minus V1. So difference, I'll get this as 0.2 volts. So when I multiply this with 1000, I'll get 200 volts. This I already explained in the previous video, so I'm just highlighting again so that you can understand. So it means I'm supposed to get an output voltage of 200 volts because the open loop voltage gain here it is of 1000. But practically I don't get this output voltage of V0 is equal to 200. I'll get a maximum, since it is a positive voltage, I'll get a positive reference voltage whatever I have connected across this reference point here. if I have connected here say 15 volts or 24 volts, so that is the maximum that I will get it. But I'll not get exactly 15 volts, I'll get approximately equal to that, because again the output voltage here, that depends on the load resistance. If higher the load resistance, the closer I'll reach to the reference voltage. So that is the meaning of the output offset voltage. Okay, so in this case, since the output voltage is plus 200 volts, it means here I am V0, I am getting of approximately say 14 volts if I connect a load resistance RL of 10 kilo ohms. If I connect a load resistance of say only 2 kilo ohms, then I may get an output voltage of 13 volts. So this is how it varies. The output saturation voltage will vary. So this is called as the maximum output voltage swing, or output offset voltage. So now let us see what is this input offset voltage. So input offset voltage, we call it as VOS in short, is the voltage that must be applied between the two input terminals such that the output voltage becomes zero. It means it is the voltage that we have to connect across the two input terminals so that the output will become 0. So typically this VOS value should be less than or equal to 2 millivolts. So now the input bias current. So input bias current is nothing but the average current across the output. So it takes the average of current entering at the two terminals, inverting and non-inverting, and takes the average, and that will give the average current across the output. So that we call it as the input base current. So if I want to write the diagram, so it is like this. Let me write the symbolic representation of Opamp. So here are my inverting and non-inverting terminals. So if the current here at V1 is, if I call this as I1, and current at the non-inverting terminal, if I call this as I2, then the I bias current, or input offset, the input bias current is nothing but I bias is equal to, that is I1 plus I2 by 2. It is an I bias is nothing but the average current of I1 and I2. Now let us talk about the input offset current. So input offset current is nothing but the difference of the two currents, that is difference of I1 and I2. So that is given as IOS, that is represented as IOS. So IOS is equal to, either I can write I2 minus I1 or I1 minus I2, because we are taking the magnitude, doesn't make any difference. So it is I1 minus I2. Even if you write I2 minus I1, it is same, because the input offset voltage will take the magnitude of it. So it is a difference of two current. That's it. Next, let us see the input impedance. So ideally we know that the input impedance is supposed to be an infinity, but practically it is very high. So again there are two types of input impedance. One is the differential input impedance and a common mode input impedance here. So let us talk about it. So let me take the Opamp symbol here again. So this is inverting, this is non-inverting terminal, and let me write one more representation here. So the two resistance here, and this is grounded. So this is inverting and non-inverting terminal. So the differential input impedance is the total resistance between the two terminals. The total resistance, if you measure between the two terminals, that is inverting and non-inverting terminal, so that we call it as, so this we call it as the differential input impedance. Differential input impedance. And if you are measuring the resistance with respect to individual terminal and making the other terminal as ground, so then we call it as a common mode input impedance. So if you, that you can see from this graph, So we are measuring the impedance, input impedance, that is the resistance between each input and ground. It means we make the one end as a grounded and we are measuring what is the resistance, and if we may ground the other terminal and if we measure the resistance across another terminal, so then that type of resistance we call it as a common mode input impedance. So this is common mode input impedance. Okay, so there is a spelling mistake here. Okay, let it be. So now let us talk about the output impedance. So ideally the output impedance is supposed to be 0, but it will be a very small value that we'll be having. So that is the output impedance. And next we'll talk about the sleeve rate. So sleeve rate is a maximum rate of change of output voltage in response to a step input voltage, is the sleeve rate of the op-amp. So that is we can get from by a simple voltage follower circuit. So let us write this. Sorry, let me clear this. And write this op-amp. So if an inverting terminal is connected to output, so your non-inverting terminal is connected to ground through a resistance R. So this is my VN, this is my non-inverting terminal, this is inverting terminal. Now this is my V out. So now if I write the graph, it means like this. If I apply a step input, that is if my Vin is a step, then the output is, it will be a slope. So that represents the change of the slope, that is represented by delta T. So this change, now this is 0 volts and this is plus V saturation, sorry, this is not V saturation, this is plus V max to minus V max. It means the sleeve rate depends on the how much time it takes for voltage to change from minus V reference voltage to plus V reference voltage, that is defined as the sleeve rate. So ideally it should be fast. So that depends, that decides the op-amp switching rate between 1 and 0 if you are talking, or if you are using these op-amps in some applications where we are using as a comparator or such kind of things where we are generating the output in terms of 0 or 1, then sleeve rate is the most important factor in such kind of applications. So it is defined as, the sleeve rate is defined as the ratio of, so that is equal to, that is delta V out by delta T. So this delta V out is nothing but this delta V out is equal to, that is V max plus V max plus V max minus of minus V max. So this is our delta V out, and delta T is the time it takes to, and the slope which it takes time to reach from minus V max to plus V max or vice versa. Okay, so this is about the sleeve rate. Okay, so we are left out with the ideal characteristic of op-amp. So this we will going to discuss in the next tutorial, because it's 19 minutes now, and we will see few examples in the coming tutorial, in the next tutorial. Okay, thank you for watching this video. Take care. Thank you.